Hi everyone, and welcome back to another episode in our quantum computing series. This episode is the first part on Shor's algorithm, covering why it is important and the core problem it solves. You don't need any specific background to follow along, just basic high school math will do for this and for the next episode on Shor's algorithm. Let's start with one of the biggest technological challenges we face in our daily lives: information security. Every day we send emails to colleagues or friends, make online transactions to buy goods, and transfer personal information over public channels that everyone could potentially access. Cryptography is the science of transforming data to ensure that only the intended recipient can read it. Suppose Alice wants to send a secret email to Bob and needs to use public information to encrypt the message. So the encryption uses Bob's public key to encrypt the plain text message to a secret message. After the encrypted message is sent over a public or private cloud service, and the cloud service sends this file to Bob, the recipient. Bob uses this private key, which only he has access to decrypt the message or reveal the secret. In this example, the public key could be Bob's public email address, and the private key could be Bob's personal password for this email address. This is an example of a public key crypto system as we use public information to encrypt the message, allowing anyone to encrypt it, but only the recipient can decrypt it. RSA is one of the most well-known public key cryptographic systems, and its security is based on the difficulty of factoring large numbers. RSA is built around two core problems: multiplication and factoring. Multiplication is a function of two inputs that produces their product as the output. For example, multiplying 3 and 5 yields an output of 15. On the other hand, factorization is a function of one input that produces two or more outputs, which are the prime factors of the input. In this video, we assume the input is simply the product of two primes. You can see that multiplication and factoring are inverse of each other. Multiplication is easy to compute, while factorization is hard to solve. Because of this, multiplication is used for verification, while factorization is used for decryption. I will explain all the details of RSA and public key cryptography in a separate video, but for now, we just need to understand the connection between Shor's algorithm and cryptography. But why is multiplication easy? Consider a simple example of multiplying 5 by 7. Consider a row of 7 marbles. 5 by 7 means to have 5 rows like that, and then count the total number of marbles. Now we want to explore why factorization is hard. Consider factoring the number 91. We need to divide 91 by all the prime numbers starting from 3. To visualize this, imagine putting every 3 marbles into a bag. If there are no marbles left at the end of this process, then the factor of 91 would be 3 and the number of bags. If there are leftover marbles, we will try to the next prime number, which is 5, and repeat the process. You see, at the end of this process, there is one marble left. So this means that 3 is not a prime factor of 91. So we need to repeat the process with 5. You can see the difficulty of factorization, especially when trying to find the prime factors of a large number. It is believed that factoring is a hard problem, and solving the factorization of a large number could take thousands of years with conventional supercomputers. Since the security of RSA relies on the hardness of this problem, if someone were to find a faster algorithm, especially one that runs in polynomial time for factorization, then RSA could be compromised. Shor's algorithm is a faster algorithm for factorization, which we will explain later. But Shor's algorithm does not solve factorization directly. Instead, it addresses the harder problem of finding period of a function, and from there, it solves the factorization. But what does harder mean in this context? Can we measure the hardness of these problems? If we can transform an instance of factorization into an instance of period finding, then we can say that period finding is harder. It means that if we can solve period finding efficiently, then we can solve the factorization efficiently. Let's consider this analogy. Suppose factorization is like finding a path from point A to point B. Without a map, this problem is very difficult because you would have to find the path through trial and error, which can take exponential time. But if you have access to a map or a navigation app like Google Map, then you can find your path easily. In this analogy, Google Map represents period finding. By having that tool, you can efficiently solve the factorization problem. But what is period finding? Consider function f from Zn to Zn that is periodic with period r. This means that the image of f at x and x plus r is the same. The goal is to find the minimum non-zero r, which is a period that satisfies this property. Let's look at an example. Consider the function f from z15 to z15 that maps each x to 2 to the x mod 15. But what does it mean? Recap. When we say a equal to b mod n, it means that a minus b is divisible by n. For example, a clock represents Z12 where everything is calculated modulo 12. For instance, 13 is equal to 1 mod 12 and 14 equal to 2 mod 12, which we know that the 13 represent 1 p.m. and 14 represent 2 p.m. Suppose f is periodic with an unknown period r, then for every integer x, we have 2 to the r plus x equal to 2 to the x mod 15. If we cancel 2 to the x from both sides, we obtain 2 to the r equal to 1 mod 15. By doing simple calculation, we find that the period r is equal to 4. This is because 2 to the 4 is equal to 16, and when we look at the modulo 15, it gives us 1. We can see this clearly since 16 minus 1 is equal to 15, which is divisible by 15. Now we will demonstrate that if we can solve the problem of finding the period, we can also solve the problem of factorization. Consider a function f that maps x to a to the x in the set of integer modulo n, denoted as Zn, and using the similar reasoning, we can see that the period r of this function must satisfy the property that a to the r equals to 1 modulo n. First, let's consider the case where the period r is an even number. Geometrically, when we say that a to the r equal to 1 modulo n, it means that if we imagine a circle with numbers from 0 to n minus 1 arranged on it, a represents one of these numbers. The number a to the 2 is another number in the circle, and so on. Our goal is to find the first power of a that returns us to 1. Now let's move 1 to the left side of the equation. We end up with a to the r minus 1 equal to 0 modulo n. We know from the difference of squares equation that a to the 2 minus b to the 2 is equal to a minus b times a plus b. Since r is even, we can apply the difference of a square to a to the r minus 1 equal to 0. If we take the greatest common divisor of n and a to the r over 2 minus 1 as p, the first prime factor, and the greatest common divisor of n and a to the r over 2 plus 1 as q, the second prime factor, then we are done. We successfully find the prime factor of n. Consider an example of factoring 15 by finding the period of 2 to the r equal to 1 modulo 15. You can see 2 to the 4 minus 1 can be split on 2 to the 2 minus 1 times 2 to the 2 plus 1, which is 3 times 5 equal to 0 modulo 15. Since the GCD of 3 and 15 is 3 and GCD of 5 and 15 is 5, then P is equal to 3 and Q is equal to 5, which are the prime factor of 15. But what if R is an odd number? In this case, we'll choose another A to find R such that A to the R is equal to 1 modulo n. But how likely are we to find an even period? The next theorem will answer this question. This theorem says that if n is the product of two prime number p and q, and a is any random number on Zn and is not equal to p and q, then with probability greater than or equal to 1 over 2, the order R of A is an even number. This theorem guarantees that if we have a large n, then with high probability we can find an A with an even order. The input of the Shor's algorithm is an integer n and a function f of A from Zn to Zn that maps each x to a to the x. And the output is the period of this function r, which means f of a on x plus r is equal to f of a on x, or equivalently, a to the r is equal to 1 mod n. The input to the factorization algorithm is natural number n. We choose a random number between a 1 and n, then find the period of a by Shor's algorithm. If r is odd, go to 1 and choose another a, otherwise go to 4. Let P be GCD of n and a to the r over 2 minus 1, and Q be GCD of n and a to the r over 2 plus 1. The output of the algorithm is P and Q, such that n is equal to P times Q. Thanks for watching this episode. In the next episode, I will discuss the technical details of Shor's algorithm and how it solves factorization using quantum circuits. Don't forget to subscribe and stay tuned.